Hello, I'm David Vošahlík. I'm here instead of Tomáš Heniš. Unfortunately, he has other duties, so he wasn't able to come. But anyway, I will present you our research activities inside our group called Smart Driving Solutions, which is based on Department of Control Engineering here at the Faculty of Electrical Engineering, but based in Karlovo náměstí, not here in Davice. Yeah, so who we are. Our group is led by the Associate Professor Tomáš Heniš. That's the person here. We are composed of mainly, or here I state that it's like 3 senior researchers, but it's more like Tomáš Heniš full-time, and then some other persons here and there, depending on the project. Then in our groups are 4 PhD students. One of them is me, and 3 others. Yeah, so our main focus is to improve vehicle dynamics, safety, stability, and also economics. That's more related to the batteries and to the battery research. So our main domain of expertise, as coming from the department, is control systems, or our control systems, and estimation and identification of models. Also including battery models. So our battery-related research activities, or our main focus, is battery SOC and SOH estimation. That's one topic. Other topic is battery management system battery management system, like system level integration, and also the BMS itself on the system level development and deployment. And we are also interested in energy management systems for EV, like electric vehicles, hybrid electric vehicles of different types, like fuel cells, plug-in hybrids, and so on. We collaborate on different projects with, for example, Garrett, then also with Formula team here in Davice, for which we have been doing last year, I think, yeah, it was last year, we have been doing a master's thesis with a student from the Formula team, which I will present here more details. Yeah, that's actually here. So regarding the master's thesis, it was meant for the e-force formula that you saw on the last picture. It has like 13 kilowatt hours and 600 volts battery. We have made like cell characterization of a single pouch cell of the battery pack from the formula. It was done here at the Department of Electrotechnology with help of them. So actually it was like, again, a collaboration with this department. We have made, here you can see the measurement setup. Actually, it was a measurement of a cell in a thermal chamber where we were measuring different characteristics, different parameters of the cell for different temperatures and different loads. Here you can see our degradation measurements. Actually, we have made just a limited number of cycles due to time constraints of the master's thesis, but we already can see some trends in it. Then here, that's other parameter that was measured. That's internal resistance of the pouch cell, different temperatures starting from 5 degrees to 55 degrees. You can see pretty much the similar pattern as for each cell, constant and then rising for depth of discharge values. Yeah, okay. So regarding the modeling that we have made there, regarding the estimation and modeling, we have used high fidelity 2RC equivalent circuit model, and we have also added a temperature model to that equivalent circuit to capture and model temperature effects. We measured open circuit voltage and internal resistance. That was regarding the measurements that I've already shown you, and then we identified the rest, the remaining parameters using optimal identification tool, and we have identified it using real driving data from some events with the formula. Then, regarding the estimation itself, we have used joint extended Kalman filter approach, where we have extended the SOC and other states of the 2RC circuit with capacity of the whole battery. And the main focus of the algorithm is to deploy it on the real-time ECU of the formula, like electronic control unit of the formula. So therefore, we have chosen simple EKF approach, which has 5 states, 4 from the 2RC circuit and 1 the added capacity, which we are trying to estimate. Here you can see how the actual algorithm worked in simulations. First, we have verified everything just using the identified model. Here you can, for example, see that we have like wrong initial estimate of our capacity. We are estimating the 13 kilowatt hours, which was the initial capacity for the battery, but the battery is already aged, which has already something like only 8 kilowatt hours or amp hours, sorry. So here it's like 10,000 seconds, which is actually quite good performance for capacity estimation, converged to the true value. Here you can see some validation on real driving data. Actually, what we had at our disposal was terminal battery voltage measurement and the ambient temperature, and also the temperature at different cells from which like some mean or maximum temperature was computed, which was in the end at our disposal on the BMS system level. Here you can see outputs of the Kalman filter and of the measured data. This is for the outputs. Those are more or less following the measured data. But here it's the interesting part, where you can see the previous method, which was rather some really simple one. And you can see that it actually quite differs from the newly developed Kalman filter, where you can see the SOC profile. And in the end, you have difference already almost like 10%. So yeah, we actually, this is quite interesting, but we have no way right now. We have no way how to verify that our Kalman filter is performing good, because the baseline algorithm, the previous method that is actually implemented there, is rather very simple. I would say it's some lookup tables based on driven kilometers or something like that. I really don't remember much about that. Yeah, that's it. And yeah, how we further want to further enhance the estimation algorithm. We also want to use unscented Kalman filter, which is I would say better from the point of view that we have like derivative-free method here, and we are not limited to do any numerical computation of Jacobians. We can directly use the lookup tables which were measured in the model and so on. We can, or what we also want to do is to make the 2RC model parameters, especially the capacity of the battery, make it temperature dependent, which was not made yet, but it should be done to make it more reliable and more accurate. And another thing we want to do is to decouple the SOC and SOH estimation. Actually, in the current approach, as we are doing that joint or the dual Kalman filtering, we are having simultaneous estimation of SOC and SOH. We want to compare it to the case where we just estimate SOC and then feed it to the health estimator, which will in turn update the parameters of the 2RC model. That's actually a thing that our colleagues were talking about in the previous days on the battery course. We are also planning a deployment of this estimation algorithm on our validation platforms, like smart driving solutions validation platforms, which is a part of next ongoing master's thesis, already in run. And again, it's in collaboration with Garrett Motion, where we also want to compare our methods with Garrett Motion methods for the SOC and SOH estimation. Yeah, so here something about our validation platforms. That's here. This one is second generation, which is already fading out, but still in use. Why fading out? Because it's too small to add there any more advanced technologies. It has space just for one e-motor, whereas we want to employ there, like for each wheel, a motor. Then, yeah, it has really many different batteries, like one for the PC, one traction battery, and so on and so forth. And it's like really not a systematic design of the whole system. Yeah, for that, we are using the next third generation subscale platform. Sorry, subscale third generation platform. It will be a bit bigger. It has like 1 meter in length and 60 centimeters wide. Still fits quite good into the car if you want to take it to some external places to measure measure something, to measure some real data. Or all wheels will be driven. All wheels are equipped with e-motor. Those are actually the e-bikes, or the small ones. I don't know how it's called actually in English. Yeah, those are the front wheels of the electric. Well, doesn't matter actually. Yeah, and all wheels will be steered. Those are the servos here for that. We have like two 38 Lion batteries, which in sum will have something like 1.6 kilowatt hours. And we have some electronic control units for that. Those are the motor inverters, some small ECUs, and the topmost one, powerful, which will be used, for example, for image processing. That's the subscale platforms, and right now we are also building a full-scale validation platform, full-scale EV. It's built on Škoda Fabia, but it's actually quite modified. You can see that here they have cut everything from the bottom where will be placed the battery. The battery which we are using is again some refactored Tesla battery. They are using, or they gave us 7 Tesla battery modules, which are connected so that it has 200 volts, approximately 35 kilowatt hours. those are the validation platforms that we want to use for the validation of all the algorithms that we are actually right now developing and validating. Again, it will have all 4 wheels driven by its individual e-motor, and each wheel should be individually steered. Yeah, and here the outlook of the activities that we are planning to do. As we are quite new in this field of battery research, we have started with that, I think, 2 years ago, the batteries itself. So actually quite new and fresh. So we want to do also a thermal management system for the validation platforms and also for the batteries. We also plan to develop our own BMS solution, more on the highest BMS level, not the cell group managers, but rather the whole integration of BMS, the one that accepts signals from cell group managers and determines SOC, SOH and such stuff. We also plan to develop energy management system for the whole vehicle that will take into account a battery and how the battery should be operated in terms of degradation, in terms of SOC, thermal management, and so on. So yeah, that's the outlook for next years. And that's all from my side. Thank you for your attention. Do you have any questions? Yeah, sure.
Yeah, you mentioned decoupling the SOC and SOH estimation.
Yes.
Do you have any concrete plans on how to do that?
Actually, what we have seen, I think it was yesterday, in the lecture by Daniel, that was actually the thing we wanted to do also earlier, but we have chosen to do the simultaneous estimation. But to the decoupled estimation, we want to estimate just the SOC. Just if I will go back, we want to have our state, just the state of the 2RC model, of the 2RC equivalent circuit model. And then, based on any technique, for example, ARX or such kind of models, whatever else, we want to estimate the parameters of the model, like capacity, internal resistance, and so on, which will tell us the state of health of the battery. And those can be then used to update our 2RC model.
So you mean 2 separate control?
Yes, yes, or estimation algorithms.
Okay.
Yeah.
Thanks.
Mm-hmm.
Yeah. Okay, may I have one question? You talk about estimation, so I understand that the challenge is to get the the best estimation possible. But what is the challenge for BMS? So far, we were not talking much about BMS. So what is the challenge if you construct BMS? Which kind of problems you are dealing with?
Actually, or what we have been talking about is the SOC and SOH estimation. That's one part of the BMS that we want to develop. Other part will be the thermal management of the whole battery. That's other part that we want to do. And third challenge is to develop any energy management system that will tell, for example, okay, right now I have at our disposal that much energy because, I'm planning to, maybe I stated it wrong. So let's start again with this third part. The third is like the energy management. For example, you know that you will be going downhill in the upcoming kilometer. So you are able to right now draw some energy because you know that you will be recuperating, you will be regenerating energy in that 1 kilometer. You also can do some optimization around that. Second thing regarding the energy management system there will be, for example, power split between the different sources, between like the combustion engine and the hybrid engines, and so on and so forth. Those are just some things coming onto my mind.
Thank you.
Yeah, so I would like to ask, so you said there are 4 states in this RC model, so
Yes.
can you elaborate what are those states?
Yeah, definitely. That's the state of charge one. Second is two of them are the voltages at these capacitors, and the fourth one is the temperature of the battery or of the cell.
Thank you. And then you said that you had some issues with obtaining SOC ground truth data.
Actually,
So
yes.
You aren't sure, like what's the right SOC. So how then you tune the filter when you don't know the ground truth regarding SOC?
Okay, we were tuning it on the identified model. So actually, we had our simulation high fidelity model for which we tuned which was identified using the real measurement data, real driving data, and also the thermal chamber cell measurements. That's how we build up our high fidelity model. For that, we tuned our EKF so that it behaves nicely in those conditions. We were trying to get as much close to the reality as possible with this high fidelity model, for which we then verified and validated our estimation algorithm. And yeah, in the end, we just employed it in the real measurement data. But we have no way how to verify that we are correct here.
Thank you.
Okay, thank you for your presentation. And next speaker should be Mr. Martinek. Is he here? No? Okay.